This simple experiment demonstrates a phenomenon that can be analyzed with the first law of thermodynamics for a closed system. For this experiment, you need a balloon, an empty beer bottle, which Sophia chugged right before she did the experiment, and an empty bucket. So Sophia is going to fill the bucket with boiling hot water and then place the bottle inside the bucket. We can anticipate that the hot water is going to heat the air inside the bottle, and this air will expand, and thus it will start inflating the balloon. And because the balloon is getting larger and the boundaries are moving outwards, we can consider this a form of boundary work. Thus, the hot water has imparted not only some heat to the system, but also a little bit of work. Ta-da! So to understand this experiment using thermodynamics, let's first make a few assumptions. Let's assume the pressure is 101 kilopascals, the volume of the bottle with a little bit of air inside the balloon is about 370 milliliters, the original temperature is room, and the final temperature is a little bit less than boiling. Air will probably act like an ideal gas, and the balloon is free to expand, so the reaction will be isobaric and pressure will be constant. A few non-assumptions are from the tables, and that R, Cp, and Cv, these are the values at 300 Kelvin. So because we assumed that air was going to act like an ideal gas, here we use the ideal gas law to find the mass of the air, which is approximately 4.41 times 10 to the negative 4 kilograms. So the first law of thermodynamics for a closed system states that the energy of the system is equal to the heat minus the work. And this comes in two flavors, an internal energy flavor and an enthalpy flavor. Now, something to note about the enthalpy is that it not only contains the internal energy, but also the boundary work. So on the right-hand side here, I've written work external because the boundary work is already contained here. So we only have work done by external forces on the system, and in this case, we have none. So W external is equal to 0. So that means that by calculating the enthalpy, we can actually find the amount of heat in the system. And also, of course, U equals CVT and H equals CPT. So substituting that in, we get two equations in terms of our temperatures. Here's some math. So here I started by calculating the enthalpy, and I got approximately 30 joules. Then I calculated the internal energy, and I got about 21.55 joules. So because the enthalpy is equal to Q, the heat, and since this term is 0, I can plug that into this equation and rearrange it to find the boundary work. So by subtracting it. So 30 joules, which is the enthalpy, minus the change in internal energy is equal to approximately 8.61 joules. So what about volume? Well, boundary work is defined as the integral from 1 to 2 of the pressure with respect to the change in volume. And since the pressure is constant, we can take it out of the integral, and that gives us basically P times delta V. And this is equal to the boundary work. So with a little bit of rearranging, we can find the delta V, which is the change in volume, which is how much the balloon inflates, and that's approximately 8.529 times 10 to the minus 5 meters cubed. Multiply that by 1,000 to convert to liters, and that gives us 0.0852 liters. And that's actually 85.2 milliliters, which is actually a pretty good approximation of what occurred in the experiment. This approximation is perhaps a little bit on the high side, but pretty close. Thanks for watching.